and welcome to this tutorial video on squaring numbers and finding square roots. First, let's look at the word square. We know that it's a four-sided shape with equal angles and side lengths, but how do we do squaring to a number? To answer that question, let's first look at what defines a square as that particular square. It's the side length or the width or a height. It's all the same thing. This is the root from which a square grows. So let's take a specific number and see how that looks. If we have three counters and we want to use them to define a square, we would use them as one side. Then we'll add additional counters to form the rest of the square. As you can see, this requires 3 rows of 3 counters, giving a total of 3 times 3 equals 9 counters. Let's see if this pattern holds for another root number. Let's square 2 counters by making a square of side length 2. This gives us a square of 2 rows of 2 counters with a total of 2 times 2 equals 4 counters. What about 1? Well, if we make a square with a single counter along each side, then we're already done. The total number of counters required is 1, which is also equal to the number of rows multiplied by the number of columns. So this is how you can square a number. Counters get a bit tricky to manage, especially for larger numbers, so we skip straight to the algebraic expression of multiplying the number by itself twice to find the area of our two-dimensional square. This is why we can also use index notation with a little number 2 as a superscript over our root number. Try squaring a few root numbers of your own and see how you go. Remember, you can always use your calculator to check your answer. Well, that takes care of squaring numbers, but what about square roots? Most of our algebraic operations have an inverse operation, and the square root is the inverse operation of squared. Effectively, square root asks the question, what would I need to square to get this answer? The question is asked by this line extending over the number for which we need to find the square root. Let's bring our counters back to explore the square root function. If we want the square root of 9, we can replace the digit 9 with 9 counters. We then form this into a square and count the number of counters along one side. This is the root of the square, or the square root. Therefore, the square root of 9 is equal to 3. Let's try another number, 4. Again, form 4 counters into a square and count the side length of 2 counters. What about 6? We can try forming 6 counters into a square, but it doesn't quite go evenly. Therefore, we know that the answer isn't a whole number. We can even find out which two whole numbers the answer lies between. We can see that we would need another 3 counters to get to the next perfect square of 9, so the square root of 6 is less than the square root of 9, so it's less than 3. We can also see that the largest complete square that we can make uses 4 counters with a few left over, so the square root of 6 is also greater than the square root of 4, so it's greater than 2. Therefore, we know that the square root of 6 lies somewhere between 2 and 3. When finding square roots, it can be really useful to know your tables so that you can recognize the perfect squares without having to try forming squares out of counters.
Thank you.